All right. Hello, everyone. Welcome back. Instrument pilot operations, AS 221, AS 252. Today we are in Unit 4A. We're going to be talking about, for this unit, we'll be talking about the pitot-static flight instruments. I should say Unit 4 has been broken into two parts, so you'll notice we're doing Unit 4A. Unit 4B, we're going to be moving on to the gyroscopic instruments, and then we'll be going on from there. But today, we're going to be focusing on the pitot-static flight instruments. So as an overview, before we get into the pitot-static system, we're going to learn about what the required equipment for IFR flight is. We'll talk about where to find that information, some acronyms to help us out with that, and then we'll get into the pitot-static system. So our objective, the student will define the requirement equipment for IFR flight, the required equipment for IFR flight. Understand and describe the pitot-static system, understand required pre-flight checks related to the pitot-static system, understand how to manage the pitot-static system failures, if any occur, and understand altitude errors related to IFR flight. This should be review. Again, this is a system that you should have gone in depth on in your private pilot ground school. So nothing should be too new to you today. So we're kind of going to review that system once again, talk about why it's even more important when it comes to instrument flight, obviously because we rely on it more, and review the errors and what to do if those errors occur. Airman Certification Standards, the ACS. Today, for this unit, we're out of Task 2B, Aircraft Flight Instruments and Navigation Equipment, as well as Task 2C, Instrument Flight Deck Check. So the applicant demonstrates the ability to identify, assess, and mitigate risks with general operation of aircraft's applicable flight instrument systems, including pitot-static instrument system, altimeter airspeed indicator, vertical speed indicator, the gyroscopic electrical and vacuum instrument system to include attitude indicator, heading indicator, and turn and slip indicator, as well as the turn coordinator, the electrical systems, the electronic flight instrument display, whether that's the PFD or the MFD, the transponder, and the magnetic compass, as well as general operation of the aircraft's applicable navigation systems to include the VOR, DME, ILS, marker beacon receiver indicators, as well as RNAV, GPS, and the Wide Area Augmentation System, or WAAS, and the FMS, as well as autopilot. So these are things that you have to demonstrate an ability to identify and assess, as well as mitigate risks. And then you have to be able to conduct an instrument flight deck check. The applicant demonstrates understanding of the purpose of performing an instrument flight deck check and how to detect possible defects, IFR airworthiness to include aircraft inspection requirements and required equipment for IFR flight, and required procedures, documentation, and limitations of flying with inoperative equipment. So what to do if something breaks. The applicant demonstrates the ability to perform pre-flight inspection to include magnetic compass, heading indicator, attitude indicator, altimeter, turn slip indicator, turn coordinator, vertical speed indicator, airspeed indicator, power source for gyro instruments. So you have to demonstrate that pre-flight inspection. So if you've been working or you've progressed through your private pilot flight course, you're probably used to checking these instruments already to make sure that they're working. But now that we are instrument pilots, we're going to be going, once you're in your flight course, you're going to be going far more in depth on checking to make sure that all of these required instruments are working. So those are the standards for this lesson. Again, these are always found in the Airman Certification Standards. Here are our references. If you want to get some additional information, the ASA, the Pilot's Manual Instrument Flying Handbook, you can buy that book. We're in chapter 3 out of that one. Or you can just use the Instrument Flying Handbook, chapter 5, talking about the flight instruments. But again, a lot of this should be review. Um, so if you have notes from your private pilot ground school or you know those references already, those are great sources to pull up if you have them. All right, so let's begin by talking about the required equipment for IFR flight. And if you remember, all the way back to private pilot, we discussed the required equipment for VFR flight. And that is found in 91.205. So here we have, this is 91.205 out of the FAR AIM. Again, it talks about, here you can see section B, talks about visual flight rules during the day. There are all of the different pieces of equipment that I'm sure you memorized. If you remember, you can either use acronyms such as A tomato flames or atoms to flee to help you memorize this list. If you keep scrolling down, eventually you'll find VFR flight rules for night. So if you intend to fly VFR at night, there's some additional equipment that you need. And if you keep scrolling down, eventually we come to the instrument flight rules. This is what is required if you intend to do an IFR flight. So very important to remember, you need everything that is listed for VFR flight, as well as all the equipment listed under instrument flight rules. So to fly IFR, your aircraft has to be equipped with this equipment. If it's not, then it is not certified for a VFR flight. So that's very important. Always make sure if you intend to do if you intend to do IFR, make sure you check that your aircraft is equipped with these systems. And it can get confusing. There's a lot of things to remember. This is also a very testable item on something like your instrument knowledge test, your FAA knowledge test, or even in your check ride. So make sure that you know this list of equipment. So we go back to our PowerPoint here. We have here's the list. This is the same list broken down two ways. So here's list number 1, list number 2 for required equipment for instrument flight. It's the same list. There are 2 acronyms you can use to remember this list. So for the first one, list number 1, we have the acronym GRAB card. So we go through each one by line. G stands for generator/alternator. So you need the ability to generate electricity in your aircraft. So G for generator. R stands for a rate of turn indicator. A stands for attitude indicator. B stands for we call it the ball or the slip skid indicator. C stands for clock. Kind of simple. Something you probably would have never thought of before, but we need a clock installed on our aircraft, whether it's digital or analog. We need a clock, but most important is it has to have a seconds function. A seconds function. So if it does not have a second hand or the digital clock does not show seconds, then it is not usable. You need it to have a seconds function. Okay, the next A stands for altimeter. So you need an altimeter with a Colesman window. So if you remember, a Colesman window is what allows us to adjust for pressure, for changes in non-standard pressure, I should say. So adjust for pressure altitude. That's what the Colesman window in the altimeter does. Next we have radios. So funny enough, radios was never required for VFR flight. It is technically not required. There are a lot of situations in VFR flight where we would need one. But technically, if you were to fly around in Gulf or class Gulf airspace, it's uncontrolled. You do not technically need a radio. Granted, good ADM says you should always have a radio, but it is not required under VFR equipment. But for IFR, it is required. So you are required to have a radio. Next, we have the directional gyro, or DG. This is it's another word for heading indicator. So your heading indicator, depending on the design, uses a gyro. Don't forget that. So that's what that last D stands for. So the acronym GRAB card, which I think is the best one, helps us remember the equipment needed for IFR flight. Remember, you're still required to have all VFR equipment plus this new list of equipment. So if you learned A-Tomato Flames or Adams to Flee, whatever you learned for VFR equipment, you can stick with that as an acronym. But now we're going to add in GRAB card. So that's a good acronym to use. And then over here on the right-hand side, in what we'll call list number 2, you can use GGG IACRA. Now, granted, this is more of a nonsense acronym. Doesn't make as much sense. But if you know maybe you do or don't know, but IACRA is like what you use to like register for tests and stuff. So it's kind of an aviation term already. And then we're just adding 3 G's out in front. So GGG IACRA. So maybe you'll remember that, maybe you won't. I don't know. So, but whichever one of these lists works better for you, that's what I would stick with. I like GRAB card, but you can use GGG IACRA if that helps you remember better. Okay, so the 3 G's, they stand for the 3 pieces of equipment that all use gyros. So the first one, we have a gyro for our AI, that stands for attitude indicator. So you can see we have attitude indicator over here in the GRAB card as well. Then we have a gyro for turn coordinator, TC, turn coordinator, or our rate of turn indicators over there. And then we have a gyro for our heading indicator, or your heading, or directional gyro. You also need an inclinometer ball. That's what your slip skid is, inclinometer ball. You need an altimeter with the Coleman window. You need a clock with seconds function. You need a radio appropriate for comm and nav. Oh, sorry, I didn't mention that before, but your radio needs to be what we call appropriate for both comm and navigation. So comm and nav. So comm is what we communicate with. That's what you talk over the radio with. And then navigation is what you would use to tune in to a VOR. So radio's appropriate for comm and nav, as well as an alternate source of power. That's what that A stands for. Okay, so that is required equipment for IFR flight. So remember, this is all found in 91.205. So if you're ever confused, go check out 91.205 and you can read through the required equipment for both VFR flight as well as IFR flight. And remember, if you're flying IFR, then you need everything. You need all VFR equipment as well as IFR required equipment. So for the rest of the day, we're going to be talking about the pitot static system. So for the rest of this unit, 4A, we're talking about the pitot static system. In 4B, we'll be talking about the gyroscopic flight instruments. So we're kind of going through the 6-pack. So 6 of the instruments use the pitot static. The others use the gyroscopic. So the pitot static system. So again, this should be reviewed. You guys have seen this before in previous courses, so we won't be going as much in depth, but we will be discussing the system. So your pitot static system gets information from your pitot tube as well as the static port. These should both be located on your aircraft. If we're flying the Cessna 172, remember the pitot tube is off your left wing. So if you look out your window on your left wing, you should see the pitot tube, that's this guy here, sticking out on your left wing. And then your static port, that's this guy all the way over here on the right, is kind of if you were on the left side of the aircraft, on the pilot side of the aircraft, kind of in front of the door, underneath, kind of below the engine cowling a little bit, but in front of the door is where you would find your static port. Okay, so those two instruments on our aircraft, and they both feed into three different instruments. Our airspeed indicator, which tells us our airspeed, our altimeter, as well as our vertical speed indicator. So airspeed tells us how fast we're going, altimeter tells us how high we are, and vertical speed indicator tells us how fast we're going up or down vertically. We know that our pitot tube takes in ram air. So if you guys can see, pull my highlighter. So you can see right here we have our ram air intake. So whenever you hear the word ram air comes up quite often when we talk about different flight instruments and different parts of the aircraft. For example, we get our air conditioning, or lack thereof, I should say, comes from ram air. So as we fly, the air that we get in our cabin is blown in through certain openings that collect ram air and blow it into our cabin. So that's how we get fresh air in our cabin. Our pitot tube collects air via the ram air hole. Let's change that to my pen. So air comes in through this ram air hole. So as we're flying along, air is just blowing over that hole and gets blown inside and then up into our instruments. So we call that ram air. That is the pitot tube. So that's really all there is to it. And then in the back, remember there is a drain hole. That drain hole is meant to drain out any water that might collect inside the pitot tube. So sometimes if it's rain or there's a lot of moisture in the air, water can start to collect inside the pitot tube. And ideally, it would just blow out the back via the drain hole. So that's important to remember because anytime we have any errors, we need to remember that that's there, and it could result in some errors if it gets blocked. So the pitot tube is directly connected to the airspeed indicator, and that's all it's connected to. The static port is connected to all three instruments. So you can see here, if we follow these tubes, the static air or the static pressure is connected to all three instruments. I would normally ask you, what do you think of when you hear the word static? And we use the word static for a couple of different things, but hopefully it would draw to mind something that is not moving. It is static. Think of like stagnant water, something that doesn't move. So static means it's not moving. So the purpose of the static port is it's just sensing the outside air pressure. So ideally, whatever the pressure is at your given altitude, that is what the static port senses. It just lets that air, that static air, into all three of these instruments. So there's nothing fancy to it. It's not ram air, right? We're not measuring how fast that air is moving. We just want to know what is the air pressure outside of our airplane. And that is what the static port senses. Okay, it feeds that information. It feeds that static air to all three instruments. And we'll talk a little bit about how each of those instruments uses the static air, but it's important to know that our one static port is connected to all three instruments. And because it's important, we also have an alternate static port inside our aircraft. So if for some reason we'll know if that gets blocked, if our static port gets blocked, we have our alternate source. All right. So that is our pitot static system. I would have this drawn somewhere, this diagram, whether that's in your notes or you take a screenshot or something. Have this somewhere, know how to draw this system, know how everything is connected, because it's going to be really helpful in visualizing how, if something gets blocked, knowing where that error might be coming from. So how all of them are connected, I think, is very important to know. All right, let's first start by talking about the airspeed indicator. So with the airspeed indicator, again, it receives what I will call its primary information from the pitot tube. Okay, again, we're getting that ram air from the pitot tube. That ram air is moving. We are measuring all the airspeed indicator is doing is measuring how fast that ram air is moving. So that's the purpose of that pitot tube. So we are taking in that ram air. And as you probably remember from your previous ground school course, that ram air travels into the pitot tube up through a series of tubes or pipes into our cockpit, into the airspeed indicator. And inside we have this diaphragm. The ram air directly fills that diaphragm. So think of like when you blow up a balloon. The harder you blow air into the balloon, the more it's going to blow up. We're creating pressure inside the balloon by blowing ram air into it. The diaphragm inside the airspeed indicator works the same way. Think of it like a balloon that we are blowing up. The harder, or I should say the faster we travel through the air, the faster we're moving, the more ram air is coming into the pitot tube, the more pressure is going to be built up inside the diaphragm, and it's going to expand. As it expands, you can see we have some mechanical linkages that translate that to airspeed. So it measures that change and translates it into airspeed. Now, if you remember, the static port is also connected. And you can see here where it says static line, that static port is connected to the case. It's connected to the case that contains all of our airspeed instrumentation. It contains that diaphragm and all this mechanical stuff. That static airline keeps the static or the pressure inside the case equal to the pressure outside of the airplane. And that's important because, think about pressure and think about trapped pressure. Think about if this case was sealed, as we go up in altitude, the pressure inside the case would increase. It would get stronger and stronger because the air pressure inside, theoretically, say we come from sea level, and as you go up in altitude, that pressure is going to expand. So now we're going to have all sorts of pressure inside this case, and that pressure would squeeze the diaphragm. So the diaphragm would not be accurate. Like as you go up in altitude, it would be less accurate because you have greater pressure around the diaphragm. We don't want that. We want to cancel that pressure out. So that's why we have that static airline. So it's very important because it cancels out static pressure. We want to cancel out static pressure. Okay, so that's the basics of how the airspeed indicator works. So if you remember, we have a couple different types of airspeed. And we can use the acronym ICE-TG, to remember those airspeeds. So first we have indicated. So there's the I in ICE. Indicated, I like to think of this as like raw airspeed data. This is the information that's coming directly to our airspeed indicator. This is what I read. So this is what you read on your airspeed indicator. Okay. We take that information and we need to calibrate it. This is where the C comes in for the ICE. So with calibrated airspeed, when we build our airplane and we have all of these pipes and everything that the airspeed indicator is connected to, there becomes some error. Now there's going to be error in the way the aircraft was built. So we call that calibrated airspeed. So calibrated is indicated, adjusted for error. Think of error when you think of calibrated. It is your indicated airspeed calibrated for any errors in the instrument. Next, we have E, which stands for equivalent. Remember, equivalent airspeed has to do with compressibility. As your aircraft goes faster, greater than, let's say, 100 knots, we start to have what's called compressibility error. The aircraft is moving so fast that there's so much air trying to get inside the pitot tube that it starts to bunch up. We get what's called compressibility. Air is compressible. So that creates an error. So remember, I'm going to try to spell compressibility. So remember, equivalent airspeed is calibrated airspeed corrected for compressibility. Okay, next we have true. This is where the T comes in. We have true airspeed, and hopefully you know this one. This is an important one. True airspeed is calibrated airspeed corrected for density altitude. Density altitude. True airspeed is calibrated airspeed corrected for density altitude. Remember, this is the one you can actually use your E6B to calculate true airspeed. And then last we have our ground speed, and that's where the G comes in. Ground speed is just true airspeed corrected for wind. Ground speed is what you actually travel over the ground. So for us, flying the Thunder Chicken, the Cessna 172, the most important airspeeds are indicated. That's what we read. Calibrated. We don't go fast enough for equivalent, so we hardly take that into account. And then we have true and ground. Okay, what's nice about the G1000, if you're flying the Cessna 172 with the G1000, is it automatically does most of this for us. It most of the time will give us all the way to true airspeed. And then even it will give us our ground speed over the ground because it's doing all of those calculations for us. So that's why the G1000 is really nice. Here's a graph that explains equivalent. So if you're a little confused on equivalent airspeed, this is showing how compressibility affects that airspeed. And then a good rule of thumb for true airspeed is it increases about 2% for every 1,000 feet above sea level. So if you want to get that's kind of like a rule of thumb to calculate what your true airspeed is or what the correction is. So you increase by 2%. Or remember, you can always use your E6B to calculate true airspeed. But again, it's nice because on the G1000, it will tell you what your true airspeed is. All right, let's talk about the altimeter. Altimeter is connected directly to the static port, and that's it. There's no other information. So how does the altimeter work? Again, this should be reviewed. We should have a good understanding at this point of how our altimeter works. But you'll notice it has very similar design features as the airspeed indicator. You can see we have that, they call it the aneroid wafer or the diaphragm, or it's just a metal container that it can expand and contract. What's very important to remember is that this diaphragm, this aneroid, is sealed. Think of it like a sealed balloon. The air that's inside is trapped there. That wafer is trapped at sea level, or a pressure of 290.92 inches of mercury. So that's where it's trapped. So if you can imagine, if you're at sea level, it's equal to the air that is on the outside of it. So if we're at sea level on a standard day, what's inside the metal diaphragm should be the same as what's on the outside. Now you'll notice the static port is connected to the case that holds the altimeter. So inside what we call the case of the altimeter, all it does is sense the outside air pressure. So as we go up in altitude, we know that the pressure should decrease. We get a decrease in pressure, which means that the pressure inside that wafer compared to the outside is going to increase. So my example that I always give is think of a balloon. So if this represents sea level, I fill up a balloon with helium at the surface. So there's my little balloon. So it's not very big. As it goes up in altitude, it's going to start to expand because the pressure outside the balloon is getting less while the pressure inside, now it's not changing, but because the pressure differential is changing. So because the pressure on the outside is decreasing, the pressure inside stays the same, the balloon starts to expand. And as it keeps going up in altitude, it's going to get even bigger because that pressure differential is going to get even greater. This is what's happening inside the little metal diaphragm inside the altimeter. As we go up in altitude, it's just going to keep getting bigger. We take that change and we measure it with all this mechanical linkage so that when we get to the altimeter, we are measuring that change in thousands of feet. Okay, and remember, the altimeter should always, for IFR flight, should always have a Kollsman window. With that Kollsman window, we adjust for current pressure. So we know we're almost never going to have a standard day. So we're always going to have to adjust for non-standard pressure. So remember, when you go to that Kollsman window and you enter, when you hear the altimeter setting over the radio, that is the altimeter setting for, it's the non-standard pressure for sea level. Not the altitude you're at, it's for the non-standard pressure at sea level. Because from sea level is where we measure everything from. All right, let's move on to, some more stuff on the altimeter. Different types of altitude. We have indicated altitude. So that's exactly whatever our indicated altitude is. That is what our altimeter is reading. There's lots of ways our altimeter can be wrong. Our altimeter needs to be adjusted. So that's something to keep in mind, is that there's a lot of errors with our altimeter. So just because it's reading something, just because it's indicating something, doesn't mean it's technically right. Then we have pressure altitude. So if you remember, pressure altitude is your field elevation corrected for non-standard pressure altitude. So in theory, if you got in the airplane and you go to the altimeter and you just automatically set it to 29902, that is going to read your pressure altitude. It's not going to be correct. Most likely it's not going to be correct, but that will read your pressure altitude. And then you hear over the radio the current altimeter setting. You set that altimeter setting, and it's going to read your field elevation. So whatever the difference is between your field elevation and your pressure altitude, that was the change in altitude from standard to non-standard pressure. Okay. Now, in terms of measuring what is actually practical to us, these two are like practical measurements to us. There's two types of altitude we use. There's true, which is our mean sea level altitude, MSL. So this is measuring above sea level. So if I have the ocean here, terrible picture. Here's my airplane way up here. When we measure above the ocean, this is our MSL, mean sea level. Now, as we go inland, here are some mountains. Again, terrible picture. Now, in terms of mean sea level, let's say our airplane has stayed at the same altitude, same MSL, but now we're above land, so this would be our AGL, So you can see our MSL hasn't changed, but our AGL has absolute above ground level AGL. So most of the time we use MSL, but it's important to know what our AGL is because we don't want to run into a mountain. Okay, so that's the difference between MSL and AGL. Now, what are the errors associated with our altimeter? First, we have temperature change. Temperature and pressure affect each other. So whenever we have a temperature change, you want to be careful about how it's going to affect your indicated altitude, so what your altimeter reads. So whether it's temperature change or a pressure change, so they're kind of connected, they're kind of the one and the same. So whether it's a temperature change or a pressure change, if you go from high to low, look out below. From high to low, look out below. So here we have two pictures that kind of shows that phenomena. If I go from 30 degrees Celsius, that's pretty hot, it's a hot day, and I fly, this is a very large change in temperature, but let's say I fly to an area that's freezing. So somehow I managed to go from 30 degrees Celsius to 0 degrees Celsius. I flew from high temperature to low temperature. I flew from high to low. We look out below. Okay, so you'll notice the indicated altitude has stayed the same. This plane has maintained the same indicated altitude by following this downward sloping line, but their true altitude has changed. It has decreased. So that's why the saying goes, if you fly from high to low, look out below, because your true altitude is going to be decreasing, while in theory, your pressure or your indicated altitude is going to stay the same. The same rule of thumb applies if we're flying from an area of higher pressure to an area of lower pressure. So you notice aircraft A here has an altimeter setting of 2992. We will consider this a high pressure. So over here we have high pressure. As the aircraft flies, now the pressure has decreased. Now we're at a pressure of 2836. We're flown into an area of low. So we've gone from high to low. So we say, look out below. So high to low, look out below. And you'll notice, again, we've maintained an indicated altitude of 5,000 feet, but our true altitude has changed from 5,000 feet to 3,500 feet. So we have to be very careful. This is why it's very important when you go on a cross country to get flight following. When you call ATC and request flight following, they give you updated altimeter settings as you fly along. So that way you always have the most up-to-date altimeter. Because we're training to be instrument pilots, you are now their priority. So when we fly instrument and we're talking to ATC, we are now the priority, which means they will always give you a updated altimeter setting whenever necessary to make sure that we're always flying the most accurate indicated altitude. So that's the goal. Okay. So things to be aware of with our altimeter. Here is a cold weather adjustment chart. You want to increase minimum altitude on instrument approaches if you're flying into a cold weather airport. So you can see here, 10 degrees plus 0. The colder it gets, because remember, we really get concerned when we go from high to low. So this is the reason you don't really see high temperatures, because when flying from high to low, that is when you're flying down. If you maintain indicated altitude, your true altitude is decreasing. So you can see here our true altitude is decreasing, flying from high to low. So we want to be careful about cold weather airports. So this chart helps us with making adjustments to our altitude. So here you can see an example. We are looking at an airport in Denver, Colorado, KAPA. This is Denver Centennial. And we want to make a correction. So we want to figure out what is our correction amount. So let's say our given airport temperature is -30. So you can see here we have an airport temperature of -30. So you can see in our chart, we've looked up -30. First, you want to take your field elevation and round to the nearest 100 feet. Okay, so this is an approach plate. So over here on the left-hand side, this is what we call an approach plate for an ILS. So we're going to learn all about this later on in the course. So it's an ILS. If you look over here, you can see our field elevation is 5,885. So we're going to round that to 5,900. We're going to identify an uncorrected altitude. So this is the altitude we would be coming in at. So let's just say we're assuming we're at 9,000 feet given this approach. 9,000 feet came from the procedure turn altitude. Again, we'll learn all about that later on. So let's just assume that's the altitude we're at. So you have to determine height above the airport. 9,000 minus 5,900 gives us 3,100 feet. And then we use the chart to determine the correct amount. So at -30, and we are we're in between 3,000 and 4,000, so we'd have to interpolate between 570 and 760, and we would get an answer of 589. So that's how much of a correction we would need to add to our altimeter when flying into cold weather airports. All right, let's talk about the vertical speed indicator. Again, the vertical speed indicator gets information from the static port. Now, I don't have a diagram of the internal workings of the vertical speed indicator here, but if you remember, the vertical speed indicator works very similarly to the altimeter, except there's one difference. Inside the case for the instrument, let's say we have that aneroid wafer, that little diaphragm, that is directly connected to the static port. So let's say this line here represents the static port. There is another line connected to the static port that also goes inside the case. But this line, this one has a calibrated leak. So there's a calibrated leak there. So what happens is inside the diaphragm senses change very quickly. It senses the change in static pressure very quickly, but the case senses that change slowly because it has a calibrated leak. So because of that, essentially what the vertical speed indicator is doing is it senses change, and it relates that change to us in a climb rate in feet per minute. So it tells us whether we are climbing, and it tells us whether we are descending. It tells us trend versus instantaneous information. So it tells us our rate of climb. So I should say this: as we start a climb, it's going to tell us our instantaneous information. So it's going to tell us whether we're climbing or descending. And then as it settles in that climb, it will tell us exactly how much or how many feet per minute we are climbing or how many feet per minute we are descending. Okay, and it does this all because of that calibrated leak. It's sensing the change in pressure. That differential allows us to find our vertical speed information. So that is the vertical speed indicator. And it is technically not required for IFR flight. So this one is not required for IFR flight. Though we have it, and it should always be there, it is not required. So some pre-flight checks. So for instrument flight, pre-flight checks, you always want to make sure your airspeed indicator is indicating 0. Your altimeter is within 75 feet of airport elevation with correct altimeter setting. And your vertical speed indicator should be pointing to 0. And anytime it's not pointing to 0, so let's say you're on the ground and that vertical speed indicator, let's say here's 0, there's like 100, negative 100. Let's say on the ground when you're not moving, it's pointing to 100. That becomes your new 0, which means 0 would represent negative 100, 200 would represent positive 100, so on and so forth. So that's the simple correction you need to do if your vertical speed indicator is not working. So let's talk about blockages. These are really important. Remember, we are now instrument pilots, so we are 100% relying on our flight instruments to tell us what is happening to our airplane. So we want these things to be working and working accurately. So what do we do if we have these different blockages? What happens if different things are blocked? So the first thing, what happens if the static port is blocked? Okay, remember static port's on the side of the plane, front left side of our Cessna 172. What happens if that gets blocked? Maybe a bug has flown into it. Maybe it gets frozen over. Whatever the case may be, if it's blocked, we would know that only the static port is blocked because our altimeter is going to be frozen. Our altimeter is going to be frozen. Whatever pressure is inside the case is going to be stuck there. It's not going to move. So your altimeter is not going to indicate any change. It will be frozen at whatever it was last at. Your VSI will move to 0 and then freeze. So it's going to move to 0 and then freeze. It's not going to change. And our airspeed indicator is going to decrease with increasing altitude. So it's going to decrease with increasing altitude. So that's what happens if our static port is blocked. If we have a blocked pitot ram air inlet, so if our pitot tube is blocked, just like in this picture, you can see this wasp. He's having a bad day. He is stuck. So our pitot tube would be blocked in this case. Our airspeed indicator will move to 0 and then freeze. So that's how we know just our pitot tube is blocked. And then last, we have our drain port. Remember, the drain port was kind of in the back of the pitot tube. If that gets blocked, then we are going to get a airspeed reading that is higher than normal, because normally our airspeed is calibrated for that leak. So that leak is designed to be there, so where it's designed to let a little bit of air out. So we get a correct airspeed reading with that hole there. And when it's blocked, now think of it as more air pressure is going to go towards our airspeed indicator, which means we're going to get a higher than normal reading. It's very important to know these blockages. What happens if these things get blocked? Because again, you are now relying on these systems to fly your aircraft. So if they're blocked, you need to be able to quickly identify what is blocked based on what you are seeing. So these different scenarios are what you're going to see in the aircraft, because the sooner you can figure out what is blocked, then you can troubleshoot it. So how do we troubleshoot these two things? So there's two ways. They don't cover every scenario. So for example, If this wasp is in our pitot tube, there's nothing we can really do about it, except hope he crawls out somehow. But if we're in flight and that little guy's in there, then we're kind of hosed. But if we do feel like our pitot heat or our pitot tube is blocked, if that happens in flight, that is most likely going to be due to icing. If that's the case, we're going to use our pitot heat to turn on, to start to heat up the pitot tube and melt the icing. So hopefully get rid of that icing. So that's one thing we can do. And then if our static port is blocked, whether it's icing or a bug or dirt or whatever gets in there, we have an alternate static source. So it's a little knob. You can see it here in this picture. It's this little red knob. When you pull that, the new static port is going to be located inside the cockpit. And the inside the cockpit is going to be warmer than outside the cockpit. So we're going to get a slightly high altimeter reading. Or in some cases, I shouldn't say it's warmer. It might be cooler inside the cockpit. So we'll get a slightly high altimeter reading because the pressure will be slightly different. So we should see a slight change in pressure. So that's what you do if you have blockages. There's really only two things you can do. You can turn on the pitot heat and melt ice. It'll only take care of ice. Or open up the alternate static source, which is located inside the aircraft. Okay, this is something we would have done if we were in class. All right, so that is the end of Unit 4A, talking about the pitot static system. So if you have any questions, any comments, any concerns, please feel free to reach out to me at my email, through the Canvas messaging, or Microsoft Teams. Any of those methods will work just fine. So thank you for listening, and let me know if you have any questions.